Directly downstream of Yankeetown Pond, in that really well-forested area down there, there are some beautiful roots in the bank that are just doing a phenomenal job in holding those stream banks together, especially down there because the access to floodplain is not as good as it is here, so all of that energy is concentrated in the channel, and which means that there's a lot of erosive power there that can do a lot of damage to the banks. But those woody roots that the trees are offering really hold that soil together and prevent it from blowing out and channel over widening, which can cause a series of instability in that reach. So it's really important to have those woody roots in the bank because they just offer so much more protection, especially if you have high bank heights. So if you had just grassy roots, like small little fibrous roots from the grass that only go down a few inches, that doesn't offer much protection to the bank. And we have seen in many situations where we have accelerated bank erosion due to the lack of root protection. It would have made a world of difference had there been a woody buffer there. And for some reason or not, it's not there anymore. For some reason, a sycamore gets blown down or falls down for some reason and it lands in the stream, it can easily just root again right where it fell, and it still provides that, that good root protection and bank stability. So it is one of the preferred tree species that we use when we try and revegetate a streamside buffer, because it does provide an excellent root structure for holding those rocks together. So here we're looking at some glacial deposits, glacial till, and it is very rich in clay-sized sediments, which can be potentially harmful for water quality. It can make the water really turbid, really muddy during high flows. And so this is something that we're really keeping a close eye out for as we're walking down the stream, because we want to get, we want to get an idea for how much of how much of the length of the stream is coming into contact with these clay-rich sediments. So we will map this with our GPS and get the length of it and the dimensions, describe the relative amount of clay in this deposit, and the kind of the setting that it's in. As it is very hard, it is very, very cohesive with all that clay sediments as well as all these little pieces of gravel, and it's actually doesn't erode as easily as, say, a bank that has a lot of sand, cobble, gravel mixture that might have been deposited there by a river a long time ago. So it is certainly a water quality issue, but something like this what we call lodgement till, won't erode quite as easily. Some other fine sediment sources that we look for and that have shown to be quite a contributing source to turbidity in our watersheds is lacustrine clay deposits, and those are deposits that were built up over time in a very large lake adjacent to a glacier. So fortunately in the Little Beaver Kill we have not found very much of that lacustrine clay, and is part of the reason why the water quality in the Little Beaver Kill has been so much better, so much cleaner than a lot of the other streams in the Catskills, because of that lack of these clay-rich deposits. I love all these like huge boulders coming out of it, because these were actually brought down by the glacier as well. There's another one sticking out right there, and it's surrounded by all these like other like this entire matrix of clay till around it. And eventually the stream will erode around these big boulders and just kind of leave the big boulders in the middle of the channel. So there's some like out in the middle of the channel over here that the stream didn't necessarily put them there. They just were eroded around over time, and because the stream doesn't have enough energy to move those big boulders, they just kind of stay there. The streams are very dynamic systems, and they don't tend to stay in one spot forever. They do erode their banks, hopefully at a slow pace and not so dramatic as we sometimes see in the Catskills. But over time they do move, and they do widen out the valley and make this nice alluvial valley. A stream bank consisting of old river deposits, alluvium, and it's actually, you can see that there is quite a mixture of material from silt and sand all the way up to large cobbles and boulders in the bank. These banks that provide a source of bedload are also important, especially if further downstream there are issues of aggradation. There being too much sediment in the stream and causing sediment to deposit excessively and create more flood hazards and concerns for maybe a downstream community or a culvert. Tropical Storm Irene, when it came in 2011 and caused all that flooding, there was large pulses of sediment that were moved by the stream from bank erosion further downstream and deposited in regions where the stream just didn't have the ability to move that volume of sediment, so it just deposited out. One example is there in Phoenicia, where the channel really aggraded and almost filled up the channel up to the Main Street Bridge there and caused a lot of additional flooding. With the possibility of, or the trend of there being more really large magnitude flood events where we're having big storms drop a lot of rain more frequently and more intensely, this can lead to more erosion issues and a lot more sediment inputs into the stream. And by sediment I mean both the suspended load, the silts and the clays, but also the bed load, the cobbles and the boulders and the gravel. That with these changing weather patterns we might see more issues with sediment getting into the stream and the stream not being able to accommodate it, not being able to handle it. We are actually recording the bank height, the bank material, the bank angle, what kind of vegetation is growing on the bank, if at all, what the stream, the vegetation buffer width is on top of the bank. So there's a lot of information that we actually collect on each eroding bank or each feature that we collect out here. So it might be bank erosion, it might be an exposure of a fine sediment source, or it might be a large woody debris jam that's causing an obstruction and impacting the stream in some way. So we are actually recording a lot of information in these GPS units, which we will analyze spatially later in the office and get a lot of statistics generated for it that will give us an overall picture of the system as a whole. And along with our GPS mapping, we are taking a lot of field notes, getting more detailed description of the reach and what, not just the bank itself, but maybe making some observations that will help us determine what is causing the erosion. In this section of the Little Beaver Kill, we're actually nearing the downstream extent, the confluence with Esopus Creek. And there's no more major tributaries flowing in at this point. This is kind of the drainage area is not going to get that much bigger. And here we are looking at a plain bed channel, meaning that it's kind of a consistent depth across the channel bed. There's not like a clear, deep bow wag on one side with deposition on the other side. It's pretty consistent depth all the way across. And we have a pretty bouldery bedload in this section. It's certainly getting steeper downstream, and the channel is getting more confined by this alluvial terrace along the right bank, and further downstream it's going to be an even taller glacial terrace bordering that bank. So it's more confined now. It's steeper, which is why we see all these boulders and cobbles in the channel bed now, because the channel actually has the ability and the energy to move this size of material. And all of these big boulders here, they're actually making a lot of really nice little pocket pools, which is good habitat diversity. And these big boulders also add a lot of roughness in the channel and kind of breaks up that flow and reduces and dissipates that energy. In the Catskills, a lot of these areas where we're getting these really massive boulders that are much bigger than the majority of the material in the stream bed, that's a pretty good indicator that they were coming from a glacial deposit of some kind, and the stream just ate around them. And so now they remain in the channel bed because the stream just isn't going to be able to move something this massive. So, a rock that's called gneiss, and it's from the Adirondack Mountains. It was brought here by a glacier, and most of the rocks that you see in the stream are actually sandstones and shales, possibly, but mostly sandstones in this area. And something like that rock, a gneiss, a metamorphic rock, was not sourced from the Catskill region. That was brought from way far up north.